Welcome back to today's live interactive session. In the last class we discussed about seepage, and we saw how to draw flow nets, and then how actually flow nets help us determine the flow uh, through a hydraulic structure. We saw that what are the properties of flow net, and how actually both the flow net is composed of the flow lines and the equipotential lines, and they are actually orthogonal to each other always. So in today's lecture also we will be discussing, we'll be revising again the flow nets a bit. We'll be going through the details of the flow nets, and then we will be uh, uh, again going through how to determine the flow using a flow net. Then we will be looking into the calculation of the seepage pressures, fluid pressures, all those things, the exit gradients, and then also we will be looking into the seepage through a art tank. Okay, so let us start. Okay, so as we know that the flow nets are nothing but the solution of the Laplace equation. The solution of the 2D Laplace equation actually gives us the flow net. Okay, so the flow net is composed of the equipotential lines and the flow lines. So these are our flow lines and these are our equipotential lines. So both of them actually form our flow net. So in order to draw a flow net, several trials are needed. So it is actually a trial and error based a procedure where just we need to draw the structure using a proper scale first. We need to draw our problem uh, with the help of a proper scale. We need to minimize it down and draw in a paper in a drawing board with the help of a proper scale, and then we need to draw the flow nets, draw the equipotential lines and the flow lines just by our own just idea, normal idea. Approximately we need to draw, and then just we need to make sure that the equipotential lines and the flow lines are always perpendicular to each other. Okay, so they intersect at right angles. So keeping these criteria in mind, we need to draw the flow nets, and if while drawing we find that those criteria are not satisfied, then we need to erase it and draw it again. And also one more important criteria that should be satisfied is that the the flow elements, that is the elements formed by the intersection of the flow lines and the equipotential lines, they should be approximately equal to squares. Okay, so these flow elements should be approximately equal to square. Okay, so this dimension should be approximately equal to the dimension. So if you see in the figure, AB and DE are our equipotential lines. So AB means this top line. So this is the AB line and this is the DE line. So this curved line is actually equipotential line. And why is it equipotential line? Because at all points in AB, the total head is H1, and the all points in the line DE, the total head is H2. So constant head along the line. That's why these are also equipotential lines. Now, if you see the flow lines intersects them at right angle. So these flow lines, they intersect this equipotential line at right angle. Okay, so these are all right angle. FG is a flow line, means this line This is a flow line because the flow can actually occur along this path, right? Okay. So below it, there is an impermeable stratum. So there cannot be any flow in that part. But above that, along the top of that impermeable layer, there can be some flow. So this FG is also a flow line. Now ACD is this ACD. So flow can also occur along the surface of the sheet pile wall. So ACD is also a flow line. Now, equipotential lines intersect FG and ACD at right angle. So these equipotential lines intersect is FG because it is a flow line. They intersect at each other at right angle. So also here they intersect each other at right angle. Now, what is a flow channel? Flow channel is actually the strip between two adjacent flow lines. So these are two adjacent flow lines. So this is a flow line. This is a flow line. So this space between them is actually known as the flow channel. So flow actually occurs through them. So it is known as flow channel. Now, if you see a zoomed image is actually given here. So these are the solid lines are our flow. These are flow lines, and these dotted lines are our equipotential lines. And the head along these equipotential lines are also given as H1, H2, H3, H4 like this. And the width and the height L1, L2, these are all same. See L1, L1. Okay, along both the directions, the dimensions are same because they're approximately squares. The Q del Q1 is the flow in this element, del Q2 is the flow in this element, del Q3. So actually all these del Q1, Q2, and Q3, these are actually all equal to del Q. Means all the flows are equal because the continuity should be maintained, right? So due to the continuity of the flow, all these flows along all these elements are actually same. Okay, so as far as law, what can you write? You can write that the flow is nothing but our K into I into area, means our hydraulic conductivity into the hydraulic gradient into the area of section of the flow, right? So del Q is nothing but K, the hydraulic conductivity into the flow H1 minus H2, the length of flow into the area. So here it's H1 to H2, higher head to lower head flow is happening. So what will be my hydraulic conductivity? It will be H1 minus H2 by the length. What is the length along which the flow is occurring? It's nothing but L1. And we are considering that there is unit cross-sectional area along the out of plane direction. That is the plane, it is the direction perpendicular to the screen, right? So it is unit cross-sectional area. So what is my area? Area is also nothing but L1 into 1, means unit length along unit length flow. Into 1. So this is our area because we are considering per meter length of the hydraulic structure. What is our flow? So you are considering unit length, per unit length. Okay. So these are all equal. See, this is del Q1. These all del Qs are equal. Nothing but K into H2 minus H3 by L2 into L2. So all these will be equal. Now all the head drops H2 minus H1, H1 minus H2, H2 minus H3. All these are actually equal to the total head drop, which is dropping from while a flow is occurring. There is some total head loss, right? Is nothing but the total head loss divided by the number of drops, potential drops. So it's nothing but equal to H by ND. So what can we write? You can write K is equal to K into this lengths will get cancelled out. So H by ND. Okay. So you can write like this. So this is the flow that is occurring through one channel. Okay. So through one flow channel, one flow channel, this flow is occurring. Okay, so there are number of flow channels. Okay, so if NF is the number of flow channel, okay, if NF is the number of flow channel, the total flow that is occurring per unit length, it will be nothing but LQ into NF into K H NF by NT. So this is the total flow that is occurring per unit length of the structure. Now, if say this length ratio, see, you're considering that this length ratio is 1, right? So if this aspect ratio is something else, say, okay, so if this aspect ratio is something else, then we can write our flow as KH ND to N. Okay, say it is slightly different than 1. Okay, then this will be the expression. Now next comes our flow nets in anisotropic soil. So anisotropic soil, what does anisotropic soil mean? Anisotropic soil means that our flow is different in both the directions. So in X direction and in Z direction, the horizontal direction by vertical direction, my coefficient of permeability or the hydraulic conductivity risk as K, that is different. Okay, so in that case, our flow lines and equipotential lines will not be perpendicular to each other. So what will be my Laplace equation then for an isotropic soil? To be KH dou square H dou H square plus K, sorry, one second. KZ dou square H by dou Z square equal to 0. Okay, so previously Kx and Kz were equal. Okay, so our equation just simplified as dou square H by dou X square plus dou square H by dou Z square. But now, as this Kx and Kz are unequal, we cannot cancel them. And also in that case, what happens is that the solution of this second order partial differential equation, the solution curve means the uh, family of curves, those family of curves are actually not perpendicular to each other. The equipotential lines and the flow lines are actually not perpendicular to each other. So what can we do is that we can write this as dou square H by Kz by Kx square plus 0. Now say we take x dash as a new x, write it as Kz by Kx into x. So after this, what happens? Our equation turns out to be as dou square H by dou x dash plus by dou Z square 0. Okay, so we are changing this x as x dash. Okay, we are transforming this x as x dash, right? So if we use this transformation, our Laplace equation then turns out to be this. And in this Laplace equation, you can see that the solution of this Laplace equation will be actually the equipotential lines and the flow lines. In this case, it will be actually perpendicular to each other. So actually, what we need to do is that if we have an isotropic soil, we need to use this transformation. We need to use this scale to actually convert it. Okay, first we will convert it, and we will then after that we will draw the equipotential lines and flow lines so that our equipotential lines and flow lines are actually perpendicular to each other. Okay. So the procedure to draw in for anisotropic soils is that we adopt a vertical scale for drawing the flow net. So we fix a vertical scale. We fix the vertical scale. In the vertical scale, so 1 centimeter is equal to 10 meter. We fix that scale and then choose the horizontal scale such that a horizontal scale is equal to kz by kx into the vertical scale. Okay, so kz by in my horizontal scale, if 1 centimeter is equal to 10 centimeter, then in the horizontal scale it will be kz by kx root over centimeter is equal to 10 meters. So we will transform it like that. We will fix our vertical scale, and the horizontal scale we will get by multiplying this term root over kz by kx into the vertical scale. And then using this new vertical and horizontal scale, we will be actually constructing the flow net as per our regular procedure. Okay, the regular procedure that we discussed back, that all they should be perpendicular to each other. The boundary conditions we discussed, and then the flow element should be actually square. So all those things we will follow, all those procedure we will follow a trial and error procedure similar to before, and then we will be drawing our flow net. So after drawing the flow net, the rate of seepage in this case will actually be given by Q is equal to over Kx into Kz to prime. So before it was, this part was, there was only single K, but now what we have to do is that our new flow will be actually given by this equation. Okay, in place of K we have 2K, so we are using equivalent K, that is equal to root over Kx into Kz. Okay. So this equation will actually give us the flow now for in anisotropic soil. now the next topic is that our uplift pressure determination. Okay, uplift pressure under a hydraulic structure. So this is a very important topic. So what happens is that when we have a hydraulic structure, say we have a earth dam, or we have any other dam, say concrete, maybe concrete dam also, anything. So what happens due to the flow of water through the soil, beneath the bed, river bed? So what happens, there is a uplift force. Okay, uplift force due to the flow of the water to the seepage of water. There is actually uplift force which acts at the base of the structure. So if the uplift force is too high, what happens is that there can be this hydraulic structure may actually fail, right? So if the uplift pressure is too high, what happens, there may be this uplift pressure is too high, it can actually shift the hydraulic structure. Also, one more thing that can happen is that there can be excessive heave. Okay, so there can be excessive heave at the end points here. So it means the soil can actually come out and form a dune-like structure. Means it can heave. Actually, that is also unfavorable. Yeah. So in that case, what happens is that from the heave, actually what happens sometimes there, uh, the soil starts getting eroded from this part. Okay, the tailing part. The soil starts getting eroded, and due to this erosion, what happens, a channel is formed. Okay, the channel is formed which gives easy passage to water. So the main purpose of construction of the dam or the hydraulic structure, which is to prevent the flow of water, is actually gets unfulfilled. So this thing actually has to be kept in check, that there is no heave, not much heat, so that there is not much piping of the this phenomenon is actually known as piping, where due to the erosion at the tail end, what happens, soil starts eroding from here due to the uplift pressure or the pressure of the soil. But when little bit slowly this whole part gets eroded, means actually there is a pipe formation. So through that pipe, through that path, water flows has easy access, easy passage. So we don't want that. Now in this uh, just a second. Yeah. So if the coefficient of permeability in x and z directions are not same, then obviously we know that it won't be perpendicular to each other. And if it is same, then it will be perpendicular to each other. So if it's not same, what we need to do is that we need to convert it, use the changed scale, we need to draw in that new scale, and then we can uh, use use this equation to determine the flow. Now, yeah. Now, if we look into this structure, so in this structure, actually, it's given that kx is equal to kz equal to k. So the soil is isotropic soil. That is, my hydraulic conductivity is equal in both the directions. Okay, so my flow is isotropic. Soil is isotropic. Now, if you look into this problem, we can see that there are total 7 number of equipotential drops. Okay, what are those 7 number of equipotential drops? From here to here, it's 1 drop. From here to here, second drop. Here to your third drop. Here to your fourth drop. Fifth drop. Sixth drop, and seventh drop. So my ND is equal to 7. Means my total number of drops are 7. Now, what is the head that is being lost? So here, if you see here, the head is 7, and here at the tailing part, the head is at 0. Right, so here the head is 0. So a total head that is lost is actually 7 meter. Okay, so in each equipotential drop, in each drop, what will be the head loss? Will be nothing but this 1 meter. So total head lost from here to here is 7, and there are 7 number of equipotential drops. So in each drop, 1 meter of head is lost. Now, what is the uplift pressure is? Uplift pressure at A. Okay, at this point, say we are asked to determine the uplift pressure. So what will be the uplift pressure? The uplift pressure is nothing but the pressure head. Uplift pressure is nothing but the pressure head multiplied by gamma W. Okay, so what is my pressure head? Pressure head is nothing but total head minus the elevation head. So total head minus elevation head into 9.81, which is my gamma W. So let us see the point A now. Okay. So it is given 1 meter, right? Yeah. So what is my total head a day? It is nothing but 7 plus 2. So this is 7 meter plus this is 2 meter. It's given here. So my total head is 7 plus 2 is equal to 9. 9. Okay. Okay. And now what is my, see, this is, you forget about this. Okay. Directly you are finding out. Total head using this one. Total head minus the drop of heads. Okay. Total head minus the drop. Total head here is 9. 7 plus 2 is 9. Right. So what is the number of drops? It is 1 from here to here. From here to here, it's some 1 drop. So this A point is lying in this equipotential line, right? In this equipotential line. So there is 1 drop. So 9 minus number of drops, it is 1 drop. 1 drop into, so what is my what is the head lost in one drop? Is nothing but 1 into 1 to 9.81. So 8 into 9.81. So this much uplift pressure is there. So similarly, if you look at B point, B point is here. B point lies in this equipotential drop. So my total head is 7 plus 2, that is 9. 9 minus how many drops? Here to here 1, here to here 1. Total 2 drops. Here to here 1 drop, and here 2 drops. So 2 into 1. So equal to 9 minus 2 into 1. Okay. So total number of drops are 2. And what is the amount of head lost in one? Each drop is 1. 2 into 1 into 9.81. So like this, we need to find out. Okay. Now, if we have to find at the point F, the point F, it will be similar. Point F is equal to 9 minus 6 into 1 into gamma W. Why 6? See, 1, 2, 3, 4, 5, and 6. At the 6th drop, my F is there. Total drops are 6. So you have 6 into 1. So 9 minus 6 into 1 into gamma W. So it will give my uplift pressure at the point F. So like that, actually, we can get uplift pressure at all the points, and then we can actually draw a diagram indicating the uplift pressures. Now, okay, so like this. So one more in another way, it can be more clear. So what I wrote is here. What I wrote here is that my pressure head is equal to total head minus the elevation head. So elevation head plus pressure head gives my total head. This thing actually we learned in the previous classes also. So we solved some of the problems where some soil layers were there, some soil was there, and then we found out the pressure head and the elevation at various points, and then we also calculate the total head. So my uplift pressure is nothing but my pressure head into my gamma W, and pressure head is nothing but total head minus elevation head. So let us see in that terms. Okay, in those terms. So actually, ultimately the thing will be same. So how this is actually coming, that I want to show. So what is my total head? Again, for A, I have to write what is my total head. So see, at A point, this here I have 7 meter is head, right? So from 7 meter, 1 meter will be lost actually when I count from here to here, right? Because one drop is happening. So my total head will be 7 minus 1 into 1, right? Total initially my head was here was 7, right? From here to here, 7 meter head loss is occurring. So my initial head was here 7 meter. From here, as I come from here to here, let me erase it and drop it. As I come from here to here in this line, there is one head drop. So each head drop 1 meter is lost. So in one head drop, 1 meter of head will be lost. Okay. So this is my total head. Total head in this point, this line, my total head is this much, minus my elevation head. So what is my elevation head? So if this is my datum, if this I am considering as datum, this A point is actually below that datum. So my elevation head will be what? -2, right? So immediately I am getting 7 minus 1 plus 2 into gamma W. The same only. So 8 into gamma W. Right. So this is how actually it's coming. So pressure head is nothing but total head minus elevation head. So from where I will get the total head. So these equipotential lines are actually lines along which along all the points my total head is actually equal. So I know the total head here. Here, this is my one of my potential is my total head is 7 meter here. Now, what will be my total head in this line? If I deduct one head drop, I will get a total head in that line. That minus the elevation. The elevation head is -2. Minus 2 will be +2. So I'm getting it like that. So similarly, it will be same. So this is one way of writing, and this is another way of writing. So this is actually, I think, this is more accurate. Okay, so this is more accurate way of correct way of writing. Directly, if I write this 9 meter here, so that is little bit wrong. So how is 9 meter is actually coming? So this is actually how my 9 meter is coming. Okay, why my 7 and 2 are added? This is actually why they are added. Okay. Yeah, so the next topic is seepage through earthen dam. So this is here you can see that it's a diagram of earthen dam. So earthen dam. So below here it is impermeable layer, and this is the earthen, right? And this is my water level. So A B C D, this line, this A B C D. Okay, this A B C D is known as the phreatic surface. Okay, so above this line there is no water, no presence of water. So we consider that there is atmospheric pressure above that line. So it is known as the phreatic surface or the phreatic line. Now A dash B C is a parabola. Okay, so we are considering that this is a parabola, and the slope of creating this line, the slope of this creating line is assumed as dz by dx. Okay, so it's assumed as dz by dx. So it's a perpendicular by base. It is dz by dx. So actually, this Casagrande actually changed this thing. So we will see that later also why he gave this I. So for now, we are taking this I as dz by dx. Okay. Yeah. So this was actually given by Dupit. Okay, Dupit gave this. So he said that the hydraulic gradient is actually constant with depth. That is, it's given by I is equal to dz by dx. Yeah. So now should I check? So I won't go through the derivation. Okay, so the derivation was actually already done in the class. So this triangle, this from this triangle we derived something. We took the triangle, um, and that from that triangle actually we took, see, I was my dz by dx. Okay, so it can be written as tan alpha. What is, where is alpha? So this is my alpha. So this tan alpha is nothing but this by this. So this can be also written as dz by dx. Now my area. So what is my q value? The q is nothing but ki into area. Okay, so I, you know, is dz by dx. K, let us keep it as k. And what is my area? Area is nothing but is c into unit length we are taking. Okay, this height into c, unit length. So we are just considering this element. Okay, then calculate the c. This area is actually nothing but L sine theta, L sine alpha into 1. Okay, so L is this length. So this derivation is actually not very easy. You can also go through it again. I won't, that's why I'm not doing it again and again. So I will directly just write the expressions. K is equal to K tan alpha L sine K L tan alpha sine alpha. Okay, so now kz dz dx. So this is also q is actually equal to kl tan alpha sine alpha. So now if we integrate this equation, integrated this equation, we can actually get the expression for L. Okay, so what is L? L is actually this length from where I'm at the so why we need L? We actually need L to find the point C. The point C actually gives us the point where my phreatic surface actually ends. So to get this point C, we need this length L. So to get this length L, we need to do all this stuff. Nothing else. Yeah. So how will we actually get this Q? So first we need to obtain alpha. So what is alpha? Let's see what is alpha. So alpha is nothing but this angle. Okay, the downstream, what is the angle? We will know this actually from the cross-section area of the dam. So we know this alpha. So this alpha is actually known to us. Then what we need to do is that we need to determine this delta. So this delta will also be known to us. How will it be known to us? Because you will be knowing the water level, right? The water level of the dam, what is there at the dam. So we'll actually be knowing this delta. Okay, so if this delta is known, we can get 0.3 delta and we can find this A dash. Okay, so we have located A dash successfully. So this A dash now you know. Now, how to calculate this D? So to calculate this D, uh, where is that D? Yeah, so how to calculate this D? D is nothing but the length from here to is A dash. So we can also find the D. So now you know D, now you know alpha. Okay, now so you can calculate this length L from the uh, from the equation that you derived here. Okay, so from the equation that you derived here, we can actually find out L. And now, as we have determined L, we can actually find a value of Q. So what will be my Q? My Q is nothing but KL tan alpha sin alpha, right? So this L we are getting from this equation. K you know, alpha you know, so you can find the flow that is occurring through this uh, dam, the seepage flow that will be occurring per meter length of this earth dam. Okay, so this way you can determine. So what we know is that we have the cross section of our dam. Okay, if we have the cross section of the dam, we will have, obviously we will have this delta, because we know the water level will have this delta, we will have the alpha value. Okay, using all these things, we'll also know the D value. We can calculate the A dash value. Okay, then we will also know the D value. Using all this, you can calculate the L, the value of this L. And if you know the L value, you will just put this L value in this equation and find out the flow. Okay, so this will finally give us the flow that is occurring through our hydraulic structure here, which is nothing but the earth dam. Okay, so this is how you need to calculate the flow through or the seepage through a earthen dam. Now, uh, now what happened is that if Casagrande told that if this alpha angle means the angle at the exit, this alpha towards the tailing side, this alpha angle is greater than 30 degrees, then this I is equal to dz by ds actually not valid. Okay, so he suggested that it's better to take I is equal to dz by ds. So what is my ds? My ds is nothing but the length of that curve. Okay, so ds is actually this length. So if I draw it again, so this is my dx, this is my dz, yes, and this length is my dz. Okay, so this is my dz. So he said that it's better to take I, my hydraulic gradient as I is equal to dz by dx. So again, using this relation, what happened? We again derived everything. So we just write it down. So again, my q is also equal to q. I is my dz by dx. Z into 1. So if I equate these two and then see if I equate these two and then integrate, we'll get the length of my L, where L is nothing but S minus S. have S is approximately equal to this. Okay, so you know H, you know D, you can find S. Then you know alpha, you know H, you know S, you can find L. And then if you put L in this equation, you can actually find the flow. Okay, similar to the previous case. Just that our expression for L is changing because the expression for my hydraulic gradient is changing here. Okay? So this was given by Casagrande. Okay, so okay, so one more thing which I will suggest you is that please go through how to draw the flow net in case of this earthen dams, how to actually construct the flow net. You can get it in any standard textbook like our Gopal Ranjan. I don't think I'm not sure if it's there, and or you can get in Aurora book also. It might be there in Aurora or any other book. So please see once how to draw flow net in case of this hydraulic structure, this kind of earthen dams. Okay, how to, so in that case actually my, my flow nets are actually like this. Okay, like this, and flow my potential lines are like this. Okay, so we can draw these things. So please see the steps how to, I will suggest that you actually go through the steps. It's how to draw flow net in case of this kind of structures once. So using the flow net also we can actually determine our this Q values, this flow values. So the next topic is that of in situ stresses. So in situ stresses, and in situ means nothing but the state. Okay, that means the native state, the natural state of the soil. What are the stresses? Okay, the natural state. What stresses are actually uh, coming into the soil particles? That is nothing but the in situ stresses. Okay, so see here in this diagram actually you can see that these are our soil particles, and up there there is actually water. The height of water is actually h. Okay, so there is depth of water above the soil is actually of capital H, and this is the water, and here we have the soil particles. Okay, and we are considering a arbitrary plane here, a plane at a depth of HA, a point A which is at a depth of HA, H suffix A from the top, right? So okay, so my total stress, okay, this total stress at this point H, point A is actually given by so A equal to H into gamma W. That is, this is the stress due to this water plus HA minus H into gamma saturated. Okay, so this the weight due to this water column plus the weight due to this soil column, right? So H into gamma W plus HA minus H means this length into the saturated humidity of the soil. Now this total stress can actually be divided into two parts. One is the uh, portion that is carried by the water. Okay, so there is water in the pores. Okay, because the soil is completely saturated, water is there in the pores, water will be there, soil is completely saturated. So due to this what happens is that some of the stress will be actually carried by the water. Okay, so that is actually known as the neutral stress. Okay, or the pore water pressure, PW. Okay, because the water is inside the pores, that's why we are calling it as pore water pressure or the neutral stress. And the other stress that will be carried by these grains. Okay, so the grains, they are into contact with each other, right? So due to the due to these contacts, the load will be transferred from grain to grain. So due to this grain to grain contact, the grains will be actually taking some of the stress. So that amount, that stress is known as our effective stress. So there are two parts of the total stress. Okay, so one is my total stress, another one is my neutral stress, another is my effective stress. Okay, so these are the two components. So now, why effective stress is important is that the main soil strength, all the concepts of the strength of soil are actually based upon this effective stress concept, because the, the, the load actually that is being carried by the soil itself, means which is actually being carried by the soil, is nothing but this effective stress, because the other part of the load is actually carried by the water, so that is actually not our concern. So what actually governs the strength of the soil, everything is our effective stress, because this is where the soil grains come into picture. That's why this effective stress is most important, and all the concepts of soil mechanics, strength concept, the shear strength, everything is based upon this effective stress concept. So what is my effective stress? So this effective stress is nothing but at all these points of contact. See, if there is, say, this is the point of contact of two grains, right? So there is some stress. Okay, so the vertical component of all these stresses, so the sum of the vertical components of all these stresses divided by the area, okay, divided by the area will actually give us the effective stress. Okay, so see, so this, see, so here we have, see, here these are the soil grains, and at the contact, these are our forces that are acting. They are the contact forces between two grains. Okay, between two grains is P1, P2, P3. These are all the contact forces. Now, this these the vertical components of all these contact forces. Okay, all these contact forces will actually have some vertical component, right? Okay, the vertical component of all this. So say this is my contact force P1. So this will have a horizontal component and a vertical component, right? Horizontal component, vertical component. So the sum of all these vertical components divided by this cross-sectional area, which is A bar will give me the effective stress. Okay. So this is the actual stress that is being taken by the soil liquids. Okay. So other part is taken by the soil. So other part is taken by the water, and the stress which is being carried by the soil grains. This is what that is. Okay. This is the effective stress. So some amount of stress is taken by the soil solutions that are contained in the water, whatever we discussed. Some of the vertical components of the contact forces of the soil solids divided by the cross-section area of the soil mass is the effective stress. Okay, we will discuss that. Now say, if AS is the cross-sectional area occupied by solid to solid contacts. Okay, so this is the cross-sectional area that is occupied by the solid to solid contacts. Okay, so this is the total cross-sectional area, that is A bar. It's the total cross-sectional area. In that cross-sectional area, some amount is occupied by void water, and that some amount of is it's occupied by the contact. Okay, the solid contacts. So if AS is the area occupied by the solid to solid contact, then what is the area that is occupied by water? It is nothing but A dash minus AS. Okay. So now if I write my total stress into A bar is equal to these things, this you can write. Okay. So total stress into A bar. So this is coming from a definition, right? Definition of the total stress. Total stress into A bar, because A bar is a total cross-sectional area. My effective stress into A bar plus U. U is nothing but a pore water pressure into the area that is occupied by water, or we can write total stress equal to effective stress plus U into pi A, right? Or we can write gamma dash plus into 1 minus A dash. So this this is actually this by this. Okay. Now if you see this A this A small as will be actually be very small compared to A bar, right? So A bar is my whole area, right? And this it is this A this is actually very small compared to my A bar. So this one actually we can neglect. So my total stress actually comes out to the effective stress plus the pore water pressure. Okay. So this ratio is very small. Okay, so almost equal to 0 because my A dash is large and my small a is very small. So this ratio will be almost equal to 0, near to 0, close to 0. So we are actually neglecting this. So finally, so what we take is that my total stress is actually equal to my effective stress plus the pore water pressure. So this is the final expression. So what is my U? What is my U? U is nothing but HA into gamma W. Okay, so if I go back to my image, what is my HA? HA is this slide. So that into gamma W will be actually giving my pore water pressure. Now let us write again. Okay, so this is my pore water pressure. Okay, and now what is my total stress? We already wrote beforehand. This is my total stress, HA into gamma W, HA into gamma W plus H minus HA into gamma saturated. Right. So what will be my effective stress? Will be nothing but total stress minus my pore water pressure. HA H into, no, this is actually H, I guess, right? This is actually H into gamma W, total height. So H into gamma W plus H minus HA into gamma set minus HA into gamma W. So if you just rearrange these terms, you will get H minus HA into gamma W plus H minus HA into gamma set. Should be minus Just a second. Just a second. Just a second. Just a second. I will just check it. H into gamma W plus sorry. It's HA minus yeah. Now it's fine. So this is my total stress and this is my pore water pressure. So total stress minus the pore water pressure, if I want to write, so it will be nothing but H minus HA minus H into gamma set minus gamma W. Now if you look, see gamma set minus gamma W is nothing but my gamma submerged. So this is finally my effective stress. Okay. So effective stress is nothing but the height of the soil column. Let us see that of the soil column. So HA minus H. This is the height of the soil column. HA minus H into gamma submerged will actually give me the effective stress. Okay. So my total stress is nothing but height of water into gamma W plus the soil height into gamma saturated. What is my pore water pressure? Pore water pressure is nothing but HA. HA is my height of what this the depth of that point from the top of the water, from the water level straight into gamma W. And what is my effective stress? Which is nothing but the height of the soil column into the submerged unit weight. So it will give me my effective stress. Okay. So now here let us see if so here you can see that there is a soil mass, and in this soil mass actually we are saying that there will be no seepage because the heads are actually same at all the points. So there is no head difference, so no seepage. So in that condition, let us find out the total stress, the pore water pressure, and the effective stress at all the points, right? So okay, so this is the first, this is this point, then we have this A point, then we have C point, then we have P point. Okay, so if you can tell me what is the total stress here at the top? Zero. Okay, zero. Now what is the total stress here at A point? What is the total stress here at A point?
H1 into gamma W.
Yeah, H1 into gamma W. So here it's H1 into gamma W. Now what is that? Okay, let us come here. Right. We'll see here. What is the total stress here at B point?
H1 into gamma W plus H2 into gamma set.
Okay. And what will be the what will be the head loss at so not the head loss, the total stress at point C? H1
H1
into gamma W plus
Z into gamma set.
into cell. Okay, so this was my total stress. Okay, so now let us come to the pore water pressures. Okay. So here what will be pore water pressure? It will
Zero.
be zero. Then at point A, at point A, same H1 into gamma W, right? At point C,
H1 plus H2 into gamma W.
H1 plus Z into gamma W. And here you are right, H1 plus H2 into gamma W. This is the progression. Next, we come to the effective stress. So effective stress, this zero, it will be zero here. Again at A point also it will be zero. Now let us come to point C. What will be the effective stress here? If it is, what will be the effective stress?
Where, sir?
At the point C, what will be the effective stress? Gamma sub into
Gamma
Z.
H1 plus Z.
Gamma
Sir,
sub into Z, right? So this minus this, if we do, it will be Z into gamma set minus gamma W. This minus this, if we do. So finally, you can write it as gamma sub into Z. Similarly, for here, what we can write? We can write H2 into gamma sub, right? So this is the case where there is no seepage. Now the next case is there when seepage is there. Actually, when seepage is there, so here we have higher head, here we have lower head. Okay, so seepage is actually coming from down to up, bottom to top, upward seepage. So similarly, we can write at this point, what is my total stress? It is zero. Okay, here what is my total stress? At the point A,
H1 into gamma W.
H1 into gamma W. At point B,
H1 plus H2 into gamma W.
total stress H1 plus H2 into gamma W, then plus H2 into gamma set, right? My total stress H1 plus H2 into gamma W plus H2 into gamma set from here. Now let us go here. We will come back to this one. This is my pore water pressure. Here it will be zero. Here it is gamma W into H1. Okay. And here it will be H1 plus H2 into gamma W. Okay. Now, actually, this is the H1 plus H2 into gamma W. This is actually the due to this stagnant part, right? Due to this this water, and what due to the extra head also one pore water pressure will be there. Okay, so nothing plus H into gamma W, small h into gamma W. Nothing but total stress H1 H2 into, sorry, Z into one. Here we watch total will be Z into gamma saturated plus H1 into gamma W. Okay. And here my product pressure will be H1 plus H2 this one is correct, right? Z into gamma saturated plus H1 into gamma W, this term. And here it will be H plus H1 plus Z into gamma W plus H is occurring, right? So plus H by H2 into Z into gamma W. I guess. So this one will be I. So it is nothing but H1 plus Z into gamma W plus IZ gamma W. Isn't it? See, total stress here at the top is 0. It's clear. At the point A, it's nothing but H1 into gamma W. This one is also simply, it is clear. Now for this C point, what will be the total stress? It will be Z into gamma saturated plus H1 into gamma W. This one is also clear. Now at the bottom, it will be H1 plus H2 into gamma W. H1 plus H2 into gamma W plus H2 into gamma Z. Plus H2 into gamma Z. This one is also clear. Now let us come to the pore water pressure. So pore water pressure at the top, it is 0. At the point A, it's gamma W plus H1, this height. Now at this point, let's see, this point, we have H1 plus H2. See, this is H1, okay? H1 plus, sorry, H1 plus Z. Okay, so H1 plus Z into gamma W plus due to this pressure is also there, right? So to this pressure, H by H2 into Z, it's given. H by H into Z, it's given to gamma W. So H by H2, I'm writing as I. So I Z gamma W. Right. Now, if I want to draw the effective stress diagram, so at the top it will be 0. At this point, it will be 0. Right. Now, what will be the at this C point? It will be I Z gamma submerged. Yes. I guess you just check this one, okay? I'm not sure because I have also not done this one doing from the first. So I'm doing here with you only. And at the bottom, it should be just a second. Wait, I will just see and then. We'll see in the book and
So at point C, Z gamma submerged minus IZ gamma W.
Z gamma sub effective stress you are saying, na?
Right, right.
Okay, Z gamma submerged minus
IZ gamma W.
yeah, correct. Yes, correct. Z into gamma submerged minus IZ gamma. Yes, correct. And at the bottom point,
H2 gamma submerged minus H gamma W.
H2 gamma submerged, H2 gamma submerged minus.
H gamma W.
So H2 is this much into gamma submerged minus. H will be small h, right? Small h
Right.
gamma W.
Right.
Yes, yes, correct, correct.
Sir, one question is there related
Yeah.
to assignment 6, which is there. In assignment 6, one problem is there. Seepage is from top side.
Mm-hmm.
So our that minus part will be it
Plus.
will be
It will,
plus, right?
yeah, here, yeah. Here it will be plus. Here, this one you are getting minus, na? This
Right,
will
right.
be plus.
Okay.
Mm-hmm. Wait, I don't know. Yeah, wait, I will just see. Downward seepage you are telling, na? It is actually there in the book. I will just wait for it. Just
It's a problem number 4 of
okay,
assignment 6.
okay. Okay, downward flow you are saying. I will just draw the downward flow. Yeah, for downward flow, see at the top it is 0. Then again it will be 0 here. Then see it will be like this. See here we got minus, right? So it will be just plus here. H into gamma sub plus H into gamma W. And at this at Z depth we will get Z into gamma sub plus IZ gamma W. This is for downward flow. Same. So actually what is happening is that during upward flow, our this one, this term is negative. Okay. The seepage pressure is actually reducing our effective stress. And when there is downwards flow, our effective stress is actually increasing due to this seepage thing. So this term is actually coming due to the seepage. Okay, this term is coming due to the seepage. So this is actually the seepage pressure. This IZ gamma W term is actually called the seepage pressure. So that is actually increasing my effective stress. So when my soil flow is occurring from top to bottom, my what happens is that the effective stress means that when the flow is occurring from top to bottom, the soil, the force between the force between the two particles are actually increasing. The stress between at the interparticular contact points are actually increasing. So downward seepage actually increases our effective stress. And what happens when the flow is upward, the effective stress actually get reduced. So at the point C, generally at no flow condition, what is my effective stress? It's Z into gamma submerged, right? So, but what is happening due to the upward seepage, this Z into gamma submerged is actually this reducing by this amount. Okay, so by this amount, my this Z into gamma submerged is actually reducing. So upward seepage is actually reducing my effective stress. So and the opposite thing happens when there is downward flow. So in no flow condition, what is my effective stress here? Nothing but Z into gamma submerged. But due to the downward flow, this seepage force is actually contributing positively to the effective stress. So my effective stress is actually increasing by IZ gamma W this amount. Okay. So yes. Yeah. So So when there is upward seepage, our effective stress actually reduces. Okay, so what is the critical hydraulic gradient? So for effective stress at Z point, what was my effective stress? So C, this was my effective stress at C point. Let me write that down. Okay, effective stress is nothing but Z. I wrote Z into gamma sub minus I Z gamma W. Right. So what is my critical hydraulic gradient? So critical hydraulic gradient is the hydraulic gradient I at which my effective stress actually becomes zero. Effective stress becoming zero means the soil losing actually the point of contact, means there is no contact between the particles. That means there is nothing, means there is no, the soil will actually flow just like water because there is no contact between the particles. You can understand that, right? So if there is no contact between the particles, it cannot take any load. The soil is actually not taking load. So this is my critical point. So if I just equate this to zero, I will get this as equal to gamma submerged by gamma W. So this is the expression for the critical hydraulic gradient. Okay, this I critical hydraulic gradient. So we need to always make sure that my hydraulic gradient is away from this critical hydraulic gradient. Okay, so for most soil, this critical hydraulic gradient actually varies from 0.9 to 1.1. So how we get this? This is that gamma submerged value. You know what is gamma submerged value? Uh, G minus 1 by 1 plus C gamma W. Okay. And so if we get ICR nothing else equal to G minus 1 plus 1 plus C. So for any soil, if you know the void ratio and if you know the G value, the specific gravity, you can find the I critical value for any soil. So we need to choose our soil and we need to compact that soil such a way that my uh, soil is actually, means there is no chance of reaching the critical hydraulic gradient. So if this critical hydraulic gradient, if it reaches, then our effective stress will become zero, and there will no, the soil cannot take any more stresses. Okay, it will just keep on flowing. So this is actually known as the quicksand condition or boiling. So why quicksand condition? So quicksand condition uh, occurs when the soil loses all its say this one effective all its strength. How it loses all its strength? Because the effective stress actually becomes zero. So the relation between the soil strength and the effective stress, this will be studying in the next the shear strength chapter. So we will see that if effective stress becomes zero, then the shear strength of the soil is actually equal to zero. So at that time actually quicksand, it is all the quick condition. Okay, quick condition because the soil has no more strength. So if you step over it, you will just get sucked into that soil. Okay, that is the quicksand condition. And boiling because see, as I told you before, this is a this art dam, right? So whatever if this at the exit, okay, if the exit say this say you're you have reached your critical gradient. So what will happen is that the soil will just keep on coming out like this. Okay, it will keep on coming, it will keep on heaving, and the water will start flowing. It will form a path. Okay, and water will just keep on flowing through this part, flowing through the soil. So it will seem as if the soil is boiling. Okay, so that's why it's known as boiling condition. So we need to always make sure that at the exit and all the points, that mainly at the tailing end, our critical hydraulic gradient is not exceeded. Yeah. So we were talking about seepage force, right? So what is by seepage force? See, I told you that if there is no flow, then at the point C, that is at the depth Z, my total stress was nothing but Z into gamma. My effective stress was nothing but Z into my gamma submerged, right? If there is upward flow, my effective stress will go Z into gamma submerged, but I into gamma this one. I into Z gamma W. If it is if the flow is downward, it will be this. Okay. So this term is actually the seepage force. Okay, the seepage, this is a seepage pressure, and if you multiply it with the cross-sectional area, you will get the seepage force. Okay, now seepage force per unit volume is given by this. Okay, I into just I into gamma W. I is my hydraulic gradient. So we can get the hydraulic gradient from the flow net at any point of time, and so if you multiply the hydraulic gradient with gamma W, you can get the seepage force. Okay, so the factor of safety in heave can be calculated from this. Heave, as I told you, means at the exit end. At the exit end, my downward force should be always be greater than the upward seepage force. Okay, otherwise what will happen? If it's high, the soil will heave. Means the soil will come out and form a dome or a dune shape structure. So you have to stop that heave. Okay, so the factor of safety against heave, it was already given to you, taught in the class. It is nothing but the weight, submerged weight of the soil that is contributing downwards to the uplift force, upward force. Okay.
Sir, heaving and boiling are two different phenomena, right?
Yes, boiling is almost same only. Like boiling is nothing but it's called when that see when say we have a structure sheet pile here like this. So what happens is that this water continues. So what happens here? See, at this point you have lost your hydraulic critical hydraulic gradient. Okay, so the soil comes out here. Then again the soil from below that will also get eroded. So a pipe like the channel is formed. Okay, so water continuously comes out from here. What happens? It's continuously it's flowing and it's pushing the soil. Okay, so that is called the boiling, because the it will seem, if you see from the top, it will seem that the bubbles will be, you can see some bubbles on the soil. uh, Actually the thing same only. Even this boiling this occurs at the same point only, when the upward seepage force is actually exceeding my downward force. At that point only this is happening. Okay, so say you don't have nothing anything here, so what happens is that it will try to push the soil here, right? So it will heave from here. So if you want to stop from heaving, you need to put some extra load over there. So you have to put some filter material over there so that this heaving is stopped. It technically means basically these things are same, but those the same thing actually is causing two different phenomena. Okay, one is actually heaving, where the soil actually just means there is a heave of the soil. Another, in the other case, what happens there, due to that due to the exceeding of the hydraulic gradient, critical hydraulic gradient, there is flow of water through which this boiling phenomenon occurs. Actually, that the point at which these two things occurs is actually the same. That is this exceeding of the critical hydraulic gradient. Just a second, I will just write. Uh, just write the equation. Yeah. So the factor of safety is given as gamma submerged by ground. So this is my hydraulic gradient. Now filters are actually used in a downstream side to increase the vector safety, as we discussed, so that this soil actually, what it allows water to pass but does not allow the soil to pass. Right. So if you don't have the filter, what will happen? The soil will actually also keep on actually the soil will also get eroded along with the pressure of the water. So this will cause heave of the soil. So to prevent the soil from coming out, what happens is that we put some material, filter material. So due to that filter material, the water is like we are allowing the water to pass, but the soil material, the material of the soil is actually stopped from passing. Okay. So due to this also, this piping or this boiling is also avoided. Okay. This the erosion is stopped. Erosion of the soil is stopped. So there is no formation of this pipe channel. So this the flow of water is also, means this channel formation also does not occur. So all this factor safety calculation and everything, this was already taught in the class. So I won't discuss. So let us start solving the problems now because it's already 7:30. Yeah, so some criteria, minimum factor of safety 4 to 5 is required. Okay. So as we discussed, the filter allows flow of water through it, but doesn't allow the soil grains to pass through it. So various criteria are available uh, to choose the correct filter material, right? And this factor of safety calculation was already discussed in the class. The factor of safety, but gamma submerged plus T1 by T2 by W. Okay, so this is the effective unit of the filter material. So initially, see, my factor of safety was this, right? But due to the use of the filter, it is increasing by this much amount. Factor of safety will be actually increasing by this much amount. So this is the benefit of using filters, and we have to ensure that the minimum factor of safety of 4 to 5 is maintained. Yeah. So now let us solve some problems. Okay, so the first problem is that for the subsoil condition shown below, determine the total stress. Neutral stress means the pore water pressure and the effective stress. Okay. So one more thing, why is pore water pressure called as a neutral stress? Is because see, we have a soil particle. So the pore water pressure actually act all around equally along a soil particle. So that's why it's known as neutral stress. Okay. Nothing. That's why the pore water pressure, other name of pore water pressure is also neutral stress. Okay. Now let us come back to the problem. So this is the subsoil condition given. So what we need to do is that we need to determine the total stress, neutral stress, and the effective stress. Okay. So first let us determine the total stresses. Okay. So what will be the total stress at A point?
0.
0. Now at B point,
uh, 3 meter into gamma W.
3 into gamma W. Gamma W? How gamma W? Water is water is here. There is no water above it.
So here there will be S value is given. So we will have to determine
The gamma
gamma.
you have to determine. Okay. So first we need to, what you need to do is that we need to determine the gamma value of the soil. Right? So what is my gamma? G plus AC 1 plus C gamma W. Right. So if you put the values, so what will be the please put G equal to 2.67, S equal to 0.4, E 0.5. Please put all the values and find the value of gamma T. This is for the sand. Gamma T. G is, my G is 2.67 plus S is 0.4, E is 0.5 divided by 1 plus 0.5 into 9.81. So it's
20.46.
18.77 I'm getting. Should be 18.77. Please check. 20. How much did you tell?
19.13, sir. It shall be
How? 2.67 plus 4.4 into
into 0.5 divided by 1 plus 0.5
uh,
into
into 10 you are taking. You take 9.81.
9.81.
81.
Okay.
Okay, na? And for gamma saturated, it will be S will be 1. So please find out this one also. It will be 20.73. Okay, similarly, let us find out for this clay also. Okay, so the clay is submerged, right? So let us find. Okay, so for similarly for clay also you can find out for the clay my water content is given. So W I know, G I know, S is will be equal to 1 because it's totally underwater, so saturated. This is my water table, completely saturated. So then I can find out gamma saturated with nothing but 17.83. Okay, now let us find out the total stress. So what will be the total stress at B? 3 into how much?
Gamma sat.
No, how gamma set?
3 into
This
gamma.
was gamma total, na 18.77. Okay, now at C, let's see what will be my total stress.
3 plus 18.77 plus
3 into 18.77 plus
gamma plus 2 into
2 into
gamma water
2 into 2 into
gamma W plus
W plus
plus 2 into
2 into
gamma gamma sat
2 into gamma set means yeah 20.73. So what will be the total? Let's see, we are finding out, right?
117.39.
I think we're making, I think this term won't come, right? 3 into 18.77 plus 2
Will
into
not
20.
come. Yeah, yes,
Yeah,
because it's
this
submerged.
term,
Yeah.
yeah, this term won't come. So what will be my gamma C?
180.69.
Now 3 into 18.77 plus 2 into 20.73. It should be 97.77. Okay. And then we have gamma total stress at D. So what we can do is directly you can see 97.77 already you know up to here, right? Just for this one you tell. It will be 4 into gamma saturated for this one, that is 17.83. So
168.69.
168.69.
Right.
Okay. Okay. Now what will be my pore water pressure at A? 0. My pore water pressure at B, again 0. What will be my pore water pressure at C?
3 into 10.
2 into gamma W. Okay. At D, 6 into gamma W.
Gamma W.
Bas, done. The total stress we have, pore water pressure we have. Now we can easily determine the effective stress. So effective stress at A equal to this minus this. Please find out. So at A point will be 0. 0 minus 0 is 0. What will be at B? 3 into 18.77 minus 0. At C, 97.77 minus 2 into gamma W. At D, 168.09. It will be 110.23. Okay.
Yes, sir.
Uh, So the next problem, we have a granular soil deposit 7-meter deep over an impermeable layer. The ground water table is 4 meter below the ground surface. The deposit has a zone of capillary rise of 1.2 meter with a saturation of 50%. Then we have to find out the variation. So let us draw the diagram. Okay, so this is my ground level. So water is here. It's 0. It is 4 meter below water is there. And it is a capillary rise of 1.2 meter. Means here there up to this much there is capillary rise. Okay. And Okay, the rest is the saturated soil up to my 7 meter. So also it is given that saturation at the zone of capillarity is 50%. Okay, so now let us first calculate see. So above this it's dry soil. Okay, here this above this it's dry soil. Here the soil is moist and here it's saturated soil. Okay, so first let us calculate my gamma d. Okay, what is the formula for gamma d? G into gamma w plus 1 by 1 plus c. So I know my G 2.65 into 9.81 by 1 plus 0.6. So it will be 2.65 into 9.81 by 1.6. It's 16.25. Okay, gamma d I got, means dry unit weight here. Then in this portion it's moist, right? So gamma moist equal to G plus AC. Now add up to 2.65 plus 0.5 into 0.651 plus 0. Okay, let's find it out. 2.65 plus 0.5 into 0.65 into 9.81. 18.08. And then saturated finally. G plus E by 1 C gamma W G plus E 19.93. Okay, so here it's dry soil, so there will be dry gamma unit weight, the unit weight will be dry, it will be used here. Here we have moist, it's given saturation is 50% in this place, and then we have our saturated. Okay, so let us find out. So at this A, B, C, and D, at all the four points, we will be calculating our total stress, effective stress, total stress, for water pressure, and the effective stress. Okay, so at A, what is my total stress? Nothing but 0. Okay, what is the pore water pressure at A?
0.
0. That, so what will be the effective stress at A? 0 minus 0 equal to 0, right? Then at B, please tell me what is the total stress at B at this point.
Height into dry density.
So what is the height?
4 minus 1.2.
Means 2.8. 2.8 into dry density was 16.
Gamma dry density.
16.25. So what is the pore water pressure? Tell me
0.
what is. No, pore water pressure won't be 0 here. Why it won't be 0 here? Because due to capillarity, my water, there will be a capillary pressure here. So capillary pressure, what happens is that,
Negative it will be. Opposite.
yeah, opposite side. This is suction pressure, right? So suction pressure, this actually contributes positively towards increase in effective stress. So that's why it's negative. So minus 1.2 into gamma W. Right. So what will be my effective stress? What will be my effective stress?
2.8 into 16.25 minus plus
Hmm?
1.2 into 9.81, right?
81. Yes.
57.27.
57.27. Okay. 57.27 per meter square. Now it's C. What is my total stress? It will be 1.2 into this moist unit weight 18.8 plus 2.8 into dry unit weight 16.25, right? What will be my pore water pressure at C? What will be the pore water pressure at C?
Can you repeat total pressure at C?
Total pressure will be this one, dry unit weight into 2.8 plus this moist unit weight into 1.2.
Okay.
What will be the pore water pressure at C?
0.
0, right? So my effective stress will be is equal to this total stress. Okay. Next at D. What is my total stress? So total stress is C plus this much. Total stress is C, you can write like total stress is C plus
Plus
3 into gamma set. Is my gamma set 126.986. What will be my pore water pressure at D?
3 into gamma W.
3 into 9.8. So my effective will be 126.986 minus 3 into 9.81. 126.986 minus 3 into 9.81. It will be 97.556 per meter square. So done this one. So now let us come to the next problem. In the next problem, it's given a soil sample, which is sand. Okay, which is sand is obtained from trench has water content of 38%. Water content is given. The specific gravity is given. We need to determine the critical hydraulic gradient of the soil. So we already discussed what is the critical hydraulic gradient. G minus 1 by 1 plus C. I also showed you how it came. So what is the this one? My critical hydraulic gradient nothing but gamma sub by gamma W. So from here we are getting this. So just put the given quantities 1 plus E. So E will be equal to nothing but W into G. So S is equal to 1. Okay, so it's saturated. So S will be 1. 2.65 minus 1 plus 1 plus 3 to 2.65. So this one comes out as 0.822. Now, also determine the maximum permissible upward gradient is a factor of safety of 3. So my factor of safety of 3 is given. So what should be my maximum permissible upward gradient? I permissible. What will be this? See, I know my critical. Okay. Critical hydraulic gradient are determined. I have determined and my factor of safety is given. So what will be my permissible hydraulic gradient?
3 into ICR.
No, y into. It will be obviously less, right? What is my factor of safety?
FO is equal to
So critical hydraulic, our permissible should always be less than the critical. Right? So FO is always I critical by I permissible. Okay, so permissible will be nothing but 0.822 by 3. nothing but 0.274. So we cannot exceed our critical, our gradient, hydraulic gradient should not be more than 0.274 if we are asked to have a vector of safety of 3. Okay. Okay, so next question is that a concrete gravity dam 120-meter long and 75-meter wide lies on a permeable soil with a coefficient of permeability this much. Okay, the head of water is maintained at 32-meter upstream and 0 at the tail end. So we have a concrete gravity dam. Okay, in the upstream, the head is maintained at 32 and at the tail end it's 0. The soil is underlain by impermeable. So here it's impermeable strata. The depth from the base of the dam to the impermeable stratum is 38 meters. So this is 38 meter. A flow net is constructed for this condition, yielded 8 flow channels and 30. So my flow channels are given. So number of flow channels, NF is equal to 8, and my number of equipotential drops is given as 18. I need to find out what is the seepage loss per day under the dam, considering a 2D flow. Right. So my K is given as 40 into 10 to the power minus 3 mm per second. So it is nothing but 40 into 10 to the power minus 3 by 1000 meter per second. Right. So what is my total head here? Head is how much is, what is the head?
32.
32 meter. So if we remember what was the expression for Q for an isotropic, homogeneous isotropic soil?
K into H into NF upon ND.
For ND, correct. So what is my K? 40 into 10 to the power minus 3 by 1000. H you already told it's 32. To NF is 8. It's given. 8 and ND is 18. Okay. So if we do this, actually, the answer will come in meter cube per second. Okay, per second per meter. So means structure is there. So per meter length of the structure per meter is the out of plane direction. Means the plane perpendicular to the screen. Means perpendicular to the screen. We are considering 1 meter. So per meter length. So this much meter cube will be, the flow will be happening per second. So they have asked how much per day. So you convert this per meter cube per second to meter cube per day. That's all. Okay. So for minus 3 by 1000. 8 by 18 into 60 to 60 into 24. So it will be 49.152 meter cube per day per meter length of the dam. Okay. So very simple. So if here everything was NF and D was given to you. Okay. So but our task is always, so our task, if this is not given, generally it won't be known to you, right? NF and ND. So what we need to do is that in a proper scale, we need to draw this diagram, draw our hydraulic structure, and then need to draw the flow lines and the flow net, and then we need to count the number of flow channels and the number of drops. Then you need to use this relation to determine the flow. Okay. Because the next one is also similar to that one. An art dam is built on an impermeable foundation with a horizontal filter at the base at the top. The permeability of the soil in horizontal. So here, previous case, it was an homogeneous isotropic soil, but here my Kx and Kz both are different. Okay. Both are different. Those are different they are. Okay. Both Kz and this Kx, they are not same. The full reservoir level is 30 meters above the filter. The flow net is constructed for the transform section, consists of 5 flow channels and 13 potential drops. So we need to estimate the seepage loss per meter length. So NF is 5 and D is 13. So please tell me what relation shall we use for this one?
Square root of
Q
kx.
is Q is equal to square root of kx into kz h nf by nd. Rest part is same, but this k is changing, right? So please calculate. Please put all the values. 3.2 to the power minus 2. What is h?
30.
30 into nf by nd. Please calculate. So please keep the units consistent. Okay. This one is in mm. This one will come in mm per second. So this 30 also you convert to mm, or this you convert to meter.
Two 52.8 mm per second.
Two, okay, 252.8
0.8 mm.
mm per second. Okay, correct, correct. I guess. 3.2 into 10 to the power minus 2 into 7. Okay. This much per meter. Okay, per meter length of flow. Okay, per meter length of the dam. Or else that also you convert it to this one mm. I guess. Else there better, it will be better if you convert this to meter. This one, okay, meter, because our flow into it's asked to us per meter length of the flow, right? So there might some inconsistency might come. So it's better, I guess, you convert everything to meter. Meter and meter per second. Okay, but still it's correct only. 252.8 mm per second per meter is correct. It's correct. So the next problem, here we have calculate CPH flow per meter of the dam, coefficient of permeability is this much. Calculate uplift pressure along the base of the dam. Compute exit gradient and factor of shifting is by the elementary square at the toe of the dam has been measured to have dimension this much. Use unit of water as 10. Okay, so one by one let us do. First let us calculate the CPH. Okay, so tell me what is H here?
6 meter.
6 meter. NF.
NF means flow channel, right?
Yeah.
3.
3. ND.
10.
10. So K is given 1.5 to the power minus 4 centimeters. So what will be the flow? So if you put all the values and make the units consistent, it will be 2.7 into 10 to the power minus 5 cubic per meter. Cubic means meter cube per second per meter. Okay. Next is to calculate the uplift pressure along the base of the wall. Okay, so let us make a table for that. So all the points, let me write A, B, C, D, E, F. Okay, all the points. Let me write here: A, B, C, D, E, F. Okay, so then we will have the number of drops. Okay, then we will have total head. Okay, total head will be nothing but 6 minus my this number of drops into the hydraulic gradient. So this will be 6 minus this number of drops into hydraulic gradient. Hydraulic gradient will be not hydraulic gradient. Yeah, hydraulic gradient nothing but 6 by not hydraulic gradient. Actually, 10 drops are total. There are 10 drops, and this 10 drops total 6 meter is lost. So in each drop, 6 by 10 is lost. So that's why 6 by 10. Okay, this is clear, right? Why 6 by 10 is here? See, total 6 meter is lost, right? And 6 meter of head is lost in 10 number of drops. So in one drops, 6 by 10 amount of head is lost, right? So that's why 6 by 10. So total head will be 6 minus number of drops into 6 by 10. Then we will have the elevation head. Then we'll have the uh, pressure head. Then we'll have the uplift pressure. Okay. So for the point A, see, approximate we have to do here. Okay, so from here to here, one drop is occurring, right? From here to here, one drop. Right. So A is here actually, this point. Okay, there here one sheet pile is there. The left side of sheet pile, this A point is there. So approximately we are taking that 0.5 drop is actually occurring. Just approximate. Okay. For the point B, B is here. B is here. So one drop here, 2, 3, 4. This is the fifth drop is here, but my B is here. Okay, so approximately you are taking as a 4.5. Okay, between fourth drop and fifth drop. Approximately you are taking at 4.5 drop. Then number C. C point you see, it's in the fifth drop, right? Fifth drop. So 5. So D, if you tell me what are the number of drops? D
6.
6. Then E 7 and F it's 8. 8 drop. F is here. Now my total head will be 6 minus 0.5 into 6 by 10. If we do this, for the first one it will be 5.7. For second one it will be 3.3. Third one it will be 3.0. Okay, 1.2. Now what is the elevation head? For A, what is the elevation head?
6 plus
No, elevation head.
minus
Minus how much?
1.
Yeah, minus 1. So for all these points, my elevation it is minus 1. Right? Because all these points are minus 1 meter below our datum. So for all these points, my elevation head is minus 1. So now what is my pressure head? Total head minus elevation head. So it will be, for first one it will be 6.7, 4.3, 4, 3.4, 2.8, 2.2, right? So what is my applied pressure? Pressure head into gamma W. Gamma W, in the question it's told to us that you can take 10. Okay, so 6.7 into 10, 57, 43, 40, 34, 28, 22. Okay, so we calculated the applied pressures. along the base. Okay. Just a second. Let's see. Yeah. Yeah. Now it's told to us compute the exit gradient. Okay, so exit gradient means the hydraulic gradient at the exit. So if the elementary square at the toe of the dam has been measured to have 2.4, means this at the toe of the dam, this length is actually measured as 2.4 meter. Okay, so what is my hydraulic gradient? Hydraulic gradient nothing but the head loss divided by the length, right? So what is the head loss? Head loss is nothing but 6/10, right? In one each drop, this much is the head loss, 6/10 divided by the length is 2.4. Okay, so if you calculate this one, it will be 0.6 divided by 2.4 by 0.25. Okay, this is my exit gradient. Now again it's asked, we need to find the factor of safety against boiling. Factor of safety against boiling. So first we need to find out the critical hydraulic gradient. Okay, so as the value of G is not given, so let us assume. So see, if the value of G is not given, so what we can do is that if you go to our theory, it see, you know that it mostly our critical hydraulic gradient mostly varies between 0.9 to 1.1. Okay, it's the real value. So in our case, we don't have the G and E value, right? So we cannot calculate the critical hydraulic gradient. So what we can do is that we can safely, let us assume that, let's say the critical hydraulic gradient is 1. Okay, varies from 1 between 1.9 and 1 to 1.1. Let us calculate safely that it's 1. So if it's 1, so what will be a factor of safety? What is the formula for factor of safety? I critical by I. So yeah, I critical by I. So what is my I critical? You can safely assume it as 1 by 0.25, which is nothing but 4. So it's fine. So our structure is actually will be safe against boiling. Okay, because our vector safety is around 4. So our structure will be safe against boiling. Okay. So a similar problem we have the next problem, this seventh problem. This is the last problem. So this is the same problems, almost same problem. So here 2 rows of sheet pile. What is that here? So all dimensions are given. 2 rows of sheet pile are driven to a depth of 4.4 meter. So this is 4.4 meter below the river bed to form a coffer dam. Okay, coffer dam. Excavation is then carried out within the coffer dam. So then we are excavating the soil out. Okay, soil out within the coffer dam up to a depth of 3.3 meter below the water level by keeping the area free from water. So we are actually pumping out the water, and this made a coffer dam using this sheet pile wall. So this is the water levels, and this is the bed, river bed, right? So we have drilled this sheet pile into the base. riverbed or the seabed, and then we are pumping out the water so that this portion is actually dry. So what happens is that actually we need to artificially pump this water out. So water is always has the tendency to flow, right? So there will be, so what we need to do is that we need to calculate how much water is actually seeping into our this dry in the coffer dam portion. How much water is actually seeping here? Actually, we need to calculate this. Manually. It is given excavation is carried out up to 3.5 meter by keeping the area free from water by pumping. The river bed is sand. This is sand. K value is given. It is underlined by impermeable strata at a depth of 6 meter. Okay, so here from so this is 6, not 6. This is 5 meter. I guess it should be 5 meter. 5 meter below the river bed. What is the quantity of flow into the coffer dam per hour per meter length of the sheet pile wall? Okay, so we need to determine the quantity of flow. So to determine the quantity of flow, our relation is same, but kh nf by nd, right? So what is my k? 3 into 10 to the power minus 3. What is my h? What is the h? What is the head difference?
3.3 minus 1.8.
No, no, it will be 3.3 only.
Okay.
Okay, so between here to here, you see the head difference, right? From here to here, the head difference will be 3.3 only. 3.3 minus 1.8 won't be 3.2 because total head from flow, because of this total. See here also the head is there, right? At this point also this head, you just calculate this total head. Will you total this length, this side, water will entering through here. Total pressure of water will be there. Will be 3.3 only. 3.3 into, so in other cases, what was there? Other cases, see, upstream one thing was there, downstream one thing was there. That's why we are deducting it. Right. So here it's 0 only considered. And here in the upstream is 3.3. So if we consider this as datum, this is 0. And in the upstream it's 3.3. So 3.3 minus 0 is 3.3. Previously, this was the datum. Here say you had x, here you had x1. So you did x minus x1. This one is the head difference between the upstream and the downstream. Now here this is my upstream and this is my downstream. So 3.3 minus 0 is will give me 3.3 only. Into NF. What is the NF? Please count the number of flow lines. I will erase it. Okay, for better view. Please the count number of flow channels.
6.
Yeah, 6. 3 from this side, 3 from this side. So total 6. And number of drops. Drops will be 11.
Right.
Total number of drops are 11. So you just calculate it. So mind the units, please. This one is in cm per second. Okay. So you can convert this into meter by multiplying -2 -5. So it will be 5.4 into 10 to the power -5 meter cube per second per meter length. Okay, per meter length of the sheet pile. So now they have asked us to calculate what is there any danger of quick condition developing at the bottom of the excavation. So here at the bottom. So please tell me, first tell me what is my this one hydraulic gradient at the exit. Means here. What is my hydraulic gradient? So total head lost is 3.3 meter across 11 drops. So in one drop from here to here, what will be the head loss? 3.3 divided by 11. right? Divided by the length it's given 0.65 meter, so 0.65 meter. If I calculate 3 by 11 divided by 0.65, will be 0.42. My exit radian. Now, if I take my I critical as 1, approximately equal to 1, what will be the factor of safety? 1 divided by 0.42 is 2.38. So, is will quicksand condition occur? No, right? Because it's less than 1 means my exit gradient is less than 1. So my quicksand condition won't occur. But the factor of safety comes out as 2.3. But it's quicksand condition won't occur. But it suggested that it should be between 4 to 5. Okay, it's better to be between 4 to 5. But our structure is safe, but it's always suggested that our factor of safety should be between 4 to 5. Okay, so was this clear? Problem clear? So this part was clear, right? First part was easy, normal, same as usual. KH and A by ND used to determine the flow, and then it was asked us to find out the whether there is any possibility of quicksand condition. So for that, first we need to do is that we need to determine the exit gradient. Okay, so the exit gradient we determine. So head loss 3.3 divided by 11 divided by this length, along which that head is being lost 0.65. So we have 0.42x my exit gradient. Then what we do is that we if I critical was given, then so here there is no mention of the G value and the E value, the wide ratio value. That's why so we are assuming the I critical value as 1, and so we see that the factor of safety is actually more than 1, so it's safe. So though it's more than 1, it's not more than 4 or 5, so it will be safe, but still it suggested that our factor safety should be between 4 to 5. What will be the answer to this question? Is there any danger of quicksand condition developing at the bottom of the excavation? The answer will be no, there is no imminent danger of any quicksand condition developing at the bottom of the condition, though a factor of safety of at least 4 to 5 is specified. Okay. Okay, so I hope this was clear. So with this, we will end today's discussion. Okay, so this problem was clear, right?
Clear.
Okay.
Thank you. Good night.
Okay, so thank you. Good night. Happy Holi.
Happy.
Uh,